Okay, good morning. I hope you had a nice break. And our lectures for the last bit of class today or this week are going to be about adding angular momentum. So our general task is to add angular momenta. Let's say J1 and J2. And when we add them, what we're really doing is we're looking at two different complete sets of commuting observables. So one is J1 squared, J2 squared, J1z, and J2z. And the basis associated with that complete set of commuting observables is called the product basis. And so if we write a state that is a common eigenstate of all of those operators, it can be labeled by J1, J2, M1, and M2. And we often put a colon between the M1 and M2. The J1 and J2 are omitted from the notation if they are understood by context of whatever problem it is that we're doing. And so we might just write this as M1, M2, if J1 and J2 are understood. Okay, and not only that, but also we might omit the colon if it's clear from the context that we are indeed talking about the product basis. So that's one complete set of commuting observables. Another one that you can use also includes J1 squared and J2 squared, but instead we'll include J squared. J is the total angular momentum and the Z component of the total angular momentum. And so that's called the total angular momentum basis. It's a different basis for the same eigenstates or the same Hilbert space. And so here we would write it as J1, J2, J, and M. But again, if J1 and J2 are understood, we often omit them from the notation. So last time in the lecture that you were asked to watch on YouTube, there was a spin 1/2 and another spin 1/2. And so we can write the process that's going on here as a tensor product of two spin 1/2 systems. So this 1/2 represents J1, this 1/2 represents J2. And so in this notation, this is equal to a spin 1 system plus a spin 0 system. So on the right side of this, that's the total angular momentum J. Okay, and so this is just a code for what we did last time that represents the two different bases. So in fact, you can write a relation between the states in the different bases. In the total spin basis, we have states that are J equals 1, M sub J equals 1, J equals 1, M sub J is minus 1, and J equals 1, M sub J equals 0. So they form a triplet. There are 3 of them. Okay, and in the product basis, we can write out what those kets are equal to. This is equal to, one way of writing it is up arrow, up arrow. So that means both spins are up in the Z basis. Okay, and this one is down arrow, down arrow. Both spins are down in this basis in the Z direction. And the 1, 0 is 1 over the square root of 2, up arrow, down arrow, plus down arrow, up arrow. Notice it matters the order because the first arrow is talking about spin 1, and the second arrow is talking about spin 2. So then there's the singlet, which is j equals 0. And m sub j, of course, then has to be 0. And this is 1 over square root of 2. It's basically the same thing, but with a minus sign. Okay, and so this is an example of what I was saying up here, that we can omit the colon if the notation makes it clear that we're talking about the product basis. So I could have written colons here, but because it's clear from the up arrow, down arrow notation that we're talking about the product basis, then it's left out. Okay, and a thing that very often occurs is that you're interested in an operator S1 dot S2, the dot product of two different spins, and that's equal to 1/2 the total spin S1 plus S2 squared minus S1 squared minus S2 squared. And it's a key fact that this operator is therefore diagonal in the total angular momentum basis and not in the product basis. It's not diagonal. And so what that means is very often, if you see the dot product of two angular momenta in general, you should be thinking that you should be using the total angular momentum basis rather than the product basis, because it's always good to choose a basis in which an important operator is diagonal. Okay, and the same thing generalizes if instead of 2 spin 1/2, I have any two angular momenta. You can always write this as 1/2 j squared minus j1 squared minus j2 squared. And so the same comment applies, that this is diagonal in the total basis, but not in the product basis. Okay, and so more generally, if you take the product of j1 and j2, the total angular momenta that you're going to get, the largest it can possibly be is j1 plus j2. And then you can have one less than that. And one less than that. So j1 plus j2 minus 2. But the smallest it can be is the difference in j1 minus j2 in absolute value. So whichever one is the largest, well, in any case, you take the difference between j1 and j2, and it has to be positive. So that's the reason for the absolute value. Okay, so for today's example, for the rest of today, we're going to do another case, which is the case of orbital plus spin. So orbital angular momentum, we traditionally write as L, and we're talking about some particle that has spin S. And so, for example, we might be interested in L dot S, which is 1/2 j squared minus L squared minus S squared. So in the total angular momentum basis, each of these operators is just going to become a number because the basis is constructed so that each of these operators has an eigenvalue in that basis. So this is going to be equal to h bar squared over 2 times j plus 1 minus L times L plus 1. And then for the spin, we can just go ahead and plug in S equals 1/2 because it's fixed. So this will be just 3/4. Okay, and then the J is either going to be L plus 1/2 or L minus 1/2. Those are the only two things it can be. because if you look at this general formula here, J2 is the spin 1/2, so that's going to be J plus 1/2, and this one's going to be J minus 1/2, and everything else in between is trivial in this case. It doesn't exist because J2 is 1/2. Okay, so in fact, let me rewrite this version of things for this special case. In this special case, we have L product with S. L has to be an integer. And S is 1/2 for a spin 1/2 particle. But this can be either one of the following two things. It can be L plus 1/2 or L minus 1/2. That's if L is greater than or equal to 1. But if L is equal to 0, then the only thing this can be is 1/2. Okay, and so those are the two possible outcomes depending on what L is. So our total angular momentum basis, I'm just going to write total basis here, consists of L plus 1/2 and M, that's really M sub J, and L minus 1/2 M. So those are eigenstates of the operator L dot S. I should say one of the reasons we're interested in the operator L dot S is because when we construct a Hamiltonian, L dot S is a term that will often occur in the Hamiltonian, for example, for atoms, with or even for the hydrogen atom, as we'll see. So the eigenvalues of this operator, we can just write down directly from this formula. Okay, so the eigenvalues are, one is h bar squared over 2. We're just going to plug in J equals L plus 1/2. So there's L plus 1/2, L plus 3/2, minus L times L plus 1, minus 3/4. And now if you multiply everything out there and simplify a little bit, this turns out to be just h bar squared times L over 2. And by the way, this group of states has degeneracy 2j plus 1, because that's the number of different M sub j's there are, which is 2 times L plus 1/2 plus 1, which is otherwise known as 2 times L plus 2. So that's the number of different states there are with L dot S eigenvalue equal to h bar squared L over 2. Okay, and then the other ones have this eigenvalue. Now I'm just going to plug in L minus 1/2 for J. Okay, but L and S are the same. And so when you multiply that all out and simplify it, it's minus h bar squared L plus 1 over 2. And here the degeneracy, so again, it's 2j plus 1. But this time 2j plus 1 is 2 times L minus 1/2 plus 1, which is otherwise known as 2L. Okay, so when we're going to construct the basis, we want 2L plus 2 states with this eigenvalue, and we want 2L states with this eigenvalue. Okay, the total number of states, the total count of the number of states is just the sum of those, which is 4L plus 2. All right, so let's write, first of all, the product basis. A notation for the product basis is we could write L S M sub L. Actually, I guess we should put a colon here. M sub S. But we're going to omit, because today we're going to be only doing this one problem. We're going to just write it as ML M sub S. But we can even do better than that, because M sub S is always plus H bar over 2 or minus H bar over 2, which we can write as up arrow or down arrow. So we'll write this as ML up arrow, omitting the colon, and ML down arrow. So ML goes from minus L to L, but the spin degree of freedom, we're just writing an arrow for that. Okay, so that's the product basis. And then our notation for the total basis is L, S, J, and M. So we're just going to write that as J and M. And we can tell the difference between the product basis, because it's not going to have up arrow, down arrows. And the product basis always will have an up arrow or a down arrow as the second entry. All right. So now, let's do the case L equals 0, because that's one is very easy. Because the bases, the product basis and the total basis in this case are the same. The bases are the same. So for example, if I write L equals 0, up arrow, in the product basis, that has total angular momentum 1/2, because L equals 0 doesn't contribute anything. And because it's angular momentum up in the Z component basis, this is 1/2, 1/2. So this is in the total basis. And the only other state with L equals 0 is 0 down arrow, which similarly is total angular momentum 1/2 and M sub J equals minus 1/2. So again, this is the product basis, but it's the same thing as this state in the total basis. Okay, and these are already eigenstates of J squared and J sub Z and L dot S. Because in the product basis, you're always in an eigenstate of L dot S. Okay, so L equals 0 was relatively easy. Let's do L not equal to 0. By the way, maybe I should pause and ask if there are any questions so far. Okay, so if L is not equal to 0, what we're going to do is we're going to start with the state M sub L, M sub S equals L up arrow. And we're going to see what happens when we act on this with various operators. So for example, J sub Z, the total angular momentum in the Z direction acting on L up arrow, is equal to L sub Z, L up arrow, plus S sub Z, L up arrow. And now the point is that we know what L sub Z acting on this state is. This is in fact just H bar L, right? So in quantum mechanics problems, a lot of what we're trying to do is we're trying to replace operators with numbers. where we can because we have some state that is an eigenstate of that operator. And similarly here, we can replace S sub z by h bar times 1/2. So the whole thing is just h bar L plus 1/2 acting on the same state. And so this is, in fact, an eigenstate of J sub z. And so the eigenvalue being h bar L plus 1/2 means that this state must have J equals L plus 1/2. So it's an eigenstate of J squared, and the eigenvalue is given by J equals L plus 1/2. The reason is the only other possibility up here, we saw it either was L plus 1/2 or L minus 1/2, and it can't be L minus 1/2 because it's J sub z eigenvalue is L plus 1/2. So we can summarize what we've learned there by saying, in the total angular momentum basis, the state L plus 1/2, L plus 1/2 is equal to, in the product basis, L up arrow. Okay, and this is representing J, M, this is representing M sub L, this is representing M sub S. So here I could have written M sub J. If you leave off the J, then it's understood to be the M for the total. Okay, so we've identified one of the states, and now the idea is to use this to construct all other states with the same value of J. So we're going to use it to construct all other states L plus 1/2 for J with all the different values of M. So maybe I should say for various M. Okay, and our strategy for this is to apply the operator J minus repeatedly. And each time we apply it, it's going to lower M by 1 unit. Okay, so recall the formula for how that works. J minus acting on a state Jm is h bar times a square root, which happens to be, there are different ways of writing it, but one way is J plus M times J minus M plus 1. And the state that it multiplies has M lowered by 1 unit. Okay, and this is equation 7.1.23 in the notes. Okay, and we're also going to use this with J replaced by L and J replaced by S. All right, so let's see how that works. Let's first apply it to this boxed equation that we have here with J equals L plus 1/2 and M equals L plus 1/2, because those are the things that appear here. Okay, so we've got J minus L plus 1/2, L plus 1/2 is equal to H bar square root of 2L plus 1 times L plus 1/2 L minus 1/2. Okay, so that's what you get when you apply this formula, plugging in for J equals L plus 1/2 and M equals L plus 1/2. Okay, and so now, so now we can call this state L plus 1/2 L minus 1/2. We're just solving for this thing on the right-hand side. So this state is equal to 1 over h bar square root of 2L plus 1. And now I'm rewriting J minus as L minus plus S minus. I'm also rewriting the state on the left-hand side using this formula. So that's where the L up arrow came from. So now the point is, on the right-hand side of this equation, in the product basis, I can evaluate each one of these. Let's do that. So L minus, acting on L up arrow, is equal to h bar square root of L plus L times L minus L plus 1, L minus 1 up arrow. Okay, I've lowered the L value by 1 unit. And this is equal to h bar square root of 2L, L minus 1 up arrow. And now I'm going to do the same thing for the S minus term. Except now the things that go in the square root are 1/2 plus 1/2, 1/2 minus 1/2 plus 1. And now it's L down arrow, so this is just h bar. Notice this, all the stuff in the square root just evaluates to 1. So this is h bar times the state L down arrow. Okay, so now we've evaluated both things on the right-hand side of this formula. Notice the h bars here are going to cancel the h bars in the denominator. And so what we end up with is we have now found the state L plus 1/2, L minus 1/2. This is in the total angular momentum basis. On the right side, we have 1 over the square root of 2L plus 1 times L down arrow plus square root of 2L, L minus 1 up arrow. All right. So we've done that. We've acted with J minus 1 time, and we found the state that has L plus J equals L plus 1/2. This is J. This is M. And now we can just keep doing that. So if we act again with J minus, let's see how it goes. So now we have J minus acting on L plus 1/2, L minus 1/2. According to our general formula for how the J minus operator acts, it has the square root, which is going to be L plus 1/2 plus L minus 1/2 times L plus 1/2 minus L minus 1/2 plus 1. All of that under the square root. Okay, and now it's one more lowered unit of J. And this stuff all evaluates to 2 and 2L. And so what we've learned is if we now solve for this state, we've got L plus 1/2, L minus 3/2 is 1 over 2 H bar square root of L. Now I'm going to rewrite my J minus as L minus plus S minus. Okay, so I've just taken this, rewritten the J minus like that, and this is still the same state. Okay, but now we're going to take that right-hand side and write it in the product basis. Okay, and we do that by the fact that we've already solved for this state right here, because that's in this boxed equation. So we're just going to plug in this. And so let's do that. So 1 over square root of 2L plus 1, L down arrow, plus square root of 2L over 2L plus 1, L minus 1, up arrow, that should be. Okay, and now the point is, we know how L minus and S minus act on these product eigenstate basis kets. And so we can just evaluate them as numbers. Let's go ahead and do that. So first we have 1 over square root of 2L plus 1 times H bar square root of L plus L, L minus L plus 1 times L minus 1 down arrow. And then the next term is, if we act on this with L minus, with S minus, we're lowering a spin that's already down, and so we get 0 for that. Right? S minus acting on a spin down state gives 0. Okay, so we've evaluated this part, and now we need to evaluate this acting on this state. Okay, so there's plus square root of 2L over 2L plus 1. H bar, I'm going to plug in what the square root is. Okay, and now this is acting on L minus 2. We've lowered the L by 1 unit. And then the last term here is what we get when we lower the spin up by 1 unit. Okay, and so first of all, the square roots are going to simplify a little bit. We can multiply these things out to get simpler numbers. And then the other thing to notice is that this is the same ket as that. And so we can add them together. And the result turns out to be 1 over the square root of 2L plus 1 times the square root of 2, L minus 1 down arrow, plus the square root of 2L minus 1, L minus 2 up arrow. Okay, so things got a little bit messy along the way, but they simplified considerably. Notice the H bars, of course, canceled. Okay, and now you can keep doing this. Keep acting with J minus. The key thing is that J minus is also equal to L minus plus S minus. And so you can evaluate it 2 different ways. That's basically what we've been doing here. Here's where we evaluated it using the J minus version. Here's where we evaluated it using the L minus plus S minus version. And so if you do that, you can actually get a general formula for these states. One way is to just keep doing it until you notice the pattern. But what you find is that in the total angular momentum basis, L plus 1/2 for any value of m, here L plus 1/2 is j, you can write like this: 1 over the square root of 2L plus 1 times the quantity square root of L minus m plus 1/2 m plus 1/2 down arrow plus square root of L plus m plus 1/2 m minus 1/2 up arrow. Okay, and this is valid for m anywhere in the range from minus L plus 1/2 up to positive L plus 1/2. Okay, and those values come from the fact that j is L plus 1/2. That's why it goes from minus j to j. Right, so this is minus j, this is j. Notice that the total angular momentum in the z direction is m, and here it's m plus 1/2 minus 1/2, and here it's m minus 1/2 plus 1/2. So in both of these terms, the total is m. Okay, any questions on that so far? All right, so by the way, the number of states that we've found so far is equal to 2L plus 2. This is out of the total of 4L plus 2. So that means there must be 2L states that we need to still find, and those states are the states with j equals L minus 1/2. And we're going to let m be anything. So this is L minus 1/2 is going to be j. So we need to find those states. So probably the easiest way to do it is to write down the most general thing it could possibly be with arbitrary coefficients and then solve for the arbitrary coefficients. So that's what we're going to do. Let's start with L minus 1/2 m. Okay, the only thing it can have is it can have m sub L equals m plus 1/2, and m sub S is down, or it can have L sub Z equals m minus 1/2, and S sub Z is up. Right, so in order to make the total be m, it either has to be m plus 1/2 here and minus 1/2 here, or m minus 1/2 here and 1/2 here. That's because the second thing has to be either plus 1/2 or minus 1/2. We're using up arrow and down arrow for plus and minus 1/2 as our code. So we can do this now by just finding these constants. So how can we find these constants? We can use the fact that we know that they must be, this state must be orthogonal to all of the states of the form L plus 1/2 m. And the reason for that is that they're all eigenstates of a Hermitian operator. So both L minus a half and L plus 1/2 with L minus 1/2 m and L plus 1/2 m are eigenstates of a Hermitian operator namely J squared, with different eigenvalues. And remember, we had a theorem that said if you have eigenstates of a Hermitian operator with different eigenvalues, then they have to be orthonormal. So the thing is, we already have one of the states. Here it is. And so we're just going to require that this be orthogonal to this, and that's going to help us solve for the coefficients. Let's just write down the inner product. Okay, and I'm going to do that without, because we're just going to be setting this equal to 0, I don't need to bother with this part, because the whole thing's going to be 0 anyway. So I have square root of L minus m plus 1/2, m plus 1/2 down arrow, plus square root of L plus m plus 1/2, m minus 1/2 up arrow. Okay, that state must be orthogonal to our L minus 1/2 state, which is A m plus 1/2 down arrow, plus B m minus 1/2 up arrow. Okay, and this inner product is 1, and so is this inner product. Okay, and this inner product of m plus 1/2 with m minus 1/2, that gives 0. And this inner product with this one also gives 0. So the whole thing just simplifies. So I should write here equals 0. That simplifies to tell us that A times square root of L minus m plus 1/2 equals minus B square root of L plus m plus 1/2. And now we have a choice to make, because we have to choose some phase for this state. And it is traditional in many books, and I'm going to follow what most books do, to choose A to be real and positive. This is known as the Condon-Shortley phase convention. There are other conventions that are possible. In principle, you could choose the complex phase of the complex number A to be anything you want, or you could even choose it to be real but negative, but we're going to choose it to be real and positive. And so what that means is the state that we're looking for is a real positive number that I'm going to call C, times this constant times m plus 1/2 down arrow, minus, that's because of this minus sign here, okay, square root of L minus m plus 1/2, m minus 1/2 up arrow. Okay, and C is real and positive. That's the Condon-Shortley phase convention choice. So the last thing we can do to find out what C is to normalize this state to unity. And so we just need to take the inner product of this state with itself. So we get C squared L plus m plus 1/2 plus C squared L minus m plus 1/2. That comes from the inner product of this with itself and with this with itself. Notice the minus sign, of course, goes away because we're squaring it. This inner product with that gives 0. Okay, so all of this should be equal to 1. And now you can solve for this to get c squared times 2l plus 1 equals 1. So c equals 1 over the square root of 2l plus 1. Okay, and so now plugging that in, L minus 1/2 m is 1 over the square root of 2l plus 1. And then the rest of this I can copy from the previous equation. Okay, so we've now found all the states in the product basis, in the total angular momentum basis, that's here, in terms of the product basis. There it is for L minus 1/2 m. And way back up here is, I should maybe draw a box around this. There it is for L plus 1/2 m. Okay, and so we've now basically finished the problem. Let me recap the problem that we've done. We found the total j squared and j sub z orthobasis states Jm as linear combinations of the product orthobasis states. Which are of the form m sub L up arrow and m sub L down arrow. All right, so basically what we've done is we've successfully carried out the process of addition of angular momentum for an orbital angular momentum and a spin 1/2. And now looking forward to next time, we're going to do the more general case where we just have any two generic J1 and J2s. But let's think about what the answer might look like. So the answer is going to be J1, J2, Jm equals some linear combination of J1, J2, M1, M2 in the product basis. So if we use completeness, we can say that what this should look like is a sum over all M1s and all M2s. There's the states that we're going to be linear combinations of, and the things that appear here, therefore, must look like this. Okay, we've basically used completeness to write this as 1, the unit operator or the identity operator. So what that means is what we're really looking for is these coefficients. These are called Clebsch-Gordan coefficients. Okay, and so we're going to try to understand how to calculate those in general. What I can say is that you can look these up in tables, but still we have to understand what the tables mean. So that's why we're going to understand the process of how you would calculate them. But there are many tables that one can find on the internet, for example, that will give you every possible combination that you would ever need of these coefficients. These are just, notice, inner products in the product basis and the total angular momentum basis, that those inner products are the same thing as the Clebsch-Gordon coefficients. Okay, and what we did today was just a special case. We did J1 equals L and J2 equals 1/2. And so from what we had, say, up here, you can read off what these various Clebsch-Gordon coefficients are, what these inner products are in the completeness relation. Okay, any questions on what we've done today? All right, so just a reminder that homework 10 is due December 3rd, which is Friday at midnight. I've been very lenient about accepting late homeworks, but not in this case because I'm going to be sending out solutions first thing on Saturday morning. So homework 10 must be turned in by midnight on Friday. Also, we've been doing classes by Zoom, but on that Friday, we're going to return just that Friday, and for the final exam, we're going to be in person. So last day of class, which is December 3rd, and the final, which is December 6th at 10 a.m. Those will both be in person, not on Zoom. Okay, and I will be handing out on Fridays, I will be giving you information about what will be on the final exam and what to study for and things like that. But it's generally going to be the same idea as the midterm, where you get to bring in your own formula sheet. All right, so that's it for today. I will see you again on Zoom on Wednesday. And let me ask again, are there any questions on any of this? All right, if not, then I will see you on Wednesday.